So we've looked at what a linear regression looks like. In particular, what a simple linear regression looks like. This is an equation that writes sales as a linear equation in advertising expenditure. Something of the form y is equal to b naught plus b1x. But where do these lines come from? What is this equation representing? And how do we know that this is a good line? How do we know that in some way it is a best fit for the data? Fit in the sense that we know that the line is not going to be perfect. It will not go through all the points. No straight line will. It is a statistical relationship. Why is this particular straight line chosen? Why is a particular straight line considered the best fit? So this line can be arrived at from a number of criteria, each good in its own way. Let's go through a little bit of the logic behind this. First, understand that we can draw multiple lines. It doesn't have to be a single line. So we have a blue line here, we have a black line here, we have another line here in a reddish hue. So we've got lots of lines. So one way to think about this problem is to say, if there are multiple lines that go through the data set, by what criteria should I pick one over the other? Which line do we choose out of all of these? Some of these, for example, this last pink line seems to be outside the data set and it seems to be ruled out. But is there a way to formalize that thinking? Which line do we choose? So how are the lines different? And can we understand the difference between the lines in the way that the lines refer to the points? Because the lines are coming from the points, or the lines have to relate to the points. They have to be in some way be close to the points. So what is the difference between these lines? The difference between these lines is that they're close to the points in different ways. So we have actual data points, actual sales, and we have the line. So we have the line and we have actual points. So one way to think about this is to say, how far are the points from the line? Now the points on the line are meant to be what? Let's go back to what the regression line is supposed to be doing. It's supposed to be doing two things. Number one, it's supposed to be saying, how does sales depend on advertising? And the second is, it's supposed to be predicting sales based on advertising. In that second form, I can say that given an advertising expenditure, there is a predicted sales. And that predicted sales is what is lying on the straight line. So I can think of the straight line as capturing the predicted sales for the input advertising expenditures. So the actual value is on the plot and the predicted value is on the line. The difference between these two, the actual value and the predicted value, for a single point, for a single region, is the prediction error. It is the error that I'm making for that particular point when I'm using the line to predict it. So the prediction error is the actual error minus the line. This prediction error, obviously, I want to be small if I want to say that the line is a good predictor of sales based on advertising expenditure. And as we just argued, that is one of the objectives of regression, being able to predict based on inputs. So now what we can do is that for all the different lines that we have, I can see this difference between the point and the line. And the difference between the point and the line is captured by these little perpendicular lines that you're seeing going from the point to the line. And you're seeing that for 4 different lines. For each of these lines, for the first few points, we haven't shown it for all the points, but for the first few points, you can see the difference between the actual point and the line. The line is what is doing the prediction. This difference, these lines, these vertical lines, which is the difference of predicted and actual, should be in some sense small. How do we quantify that? So there are multiple data points to consider. We're looking at only a few of them. But this points to another problem. And the problem is that somehow there needs to be an aggregation of these differences. All these differences, difference between what and what, difference between actual and predicted, have to be aggregated over, added over, averaged over, somehow. Added is the easiest thing to do. So it has to aggregate over the multiple data points. So it's to aggregate the errors across all the data points. So we have to look at this error, we have to make the error small, and we have to aggregate the error over all the data points. The line with the least aggregate error across all the data points is the one that we want. Least aggregate error. But we haven't told you how to aggregate yet, what to take the least off. So now we need to quantify this statement of the least aggregate error. Over all the points, when is my predicted error the smallest? Equivalently, when is it that I'm predicting sales the best, given advertising as a predictor? This line is called the best fit line. What we'll need to look at is how we can find this best fit line using criteria that make sense of this aggregate idea and give a clear definition of what it is that we are taking the least of.